Audio. Hello, Strength and Material students. I think I see Brendan. Hey, Brendan.
Hey Vince, how you doing,
Hey,
Mr. Griffin?
doing good, Brendan.
Good.
You might be my only
No,
customer.
we got Ben Seaman, Ben Harris, and Ashley Pennyman in here.
Wow, fantastic.
Mm-hmm.
I'm trying to get my picture on this computer here. Not having a whole lot of luck. Okay. Hey, wait a minute. Come on now. Unpin video. Press escape or double click. Or double click to exit full. I don't want to exit full screen mode. I don't want that picture there either. I don't know what I want. Hey, I like that mountains in the background. A helicopter there, Brendan.
Yeah, that was where I was deployed.
Where was it?
Afghanistan, Kunar province.
Kumar?
Kunar in Afghanistan, so it's like
Kunar.
their provinces there.
Kumar. I'll ask my son-in-law. He was in Afghanistan.
Oh, right on.
He was a paratrooper guy.
Oh, awesome. I love those airborne guys. They're definitely needed.
Did you jump out of airplanes too?
No, I was air assault, so I jumped out of. I actually repelled from helicopters, so did
Well,
Chinooks.
that'll work.
Yeah, that'll do too. It's pretty
Well,
fun,
I did
pretty
my
exhilarating.
thing 50 years ago in Vietnam, Brendan.
Oh, well, thank you for that. You're definitely one of the reasons why I joined. So appreciate our
Thank
Vietnam
you.
veterans.
I
Yeah,
appreciate what you did too. But right now, Brendan, I got to figure out how to get my picture on here.
yeah. So maybe
Uh,
if you look at the bottom left corner, for me, there's a mute in a video
oh,
button.
wait a minute. It says start video. Maybe that's what I need.
Yeah, just click that, and then it'll pop up. There you go.
Yeah. Hey, oh, wait a minute. I clicked it and then,
Yeah, don't know.
okay.
There you go.
Yeah, that's better. Okay. That's really not too terribly bad right there. That looks pretty good. You can read that. Yeah. Hey, are you completely out, Brendan? It's Brendan.
Yes, sir. Yep,
Brendan.
I am. I am. Yeah, I'm out of the army. Been out since 2014, and just been doing my thing since then.
It feels good to be completely out, doesn't it?
Right? There's a saying, what they call it. It's from your generation. It's called "Been there, done that. Don't want to go back."
Yeah, it's a wonderful feeling.
Yes, sir.
Well, let's see here. I think we're almost ready to rock and roll here. How about it? Let's see who's on board here. We got a great crowd. Alex, Nicholas, Ashley, Brendan, Mohammed, Braxton, Ben, Ben, good crowd. Anybody out there have a question for me? Uh-oh, it's 9:30. We need to get started. Anybody have a question before we start?
Is our test coming up? Is that I saw it is on the schedule for today?
Yeah,
Um,
it's available today, and I think it's due Friday at midnight. I believe that's right.
so it's a take-home test. We don't need to
Yeah,
schedule an
take home, open
examination.
book. Yeah,
Yes, sir. Too easy.
yeah, you'll do great. But I got to looking at it, and there's some stuff on chapter 3 on there. I guess I was ambitious and thought we'd get that far. So I need to talk to you a little bit about chapter 3 so you can survive that question on chapter 3. So that's what I want to do right now. I was going to just have a nothing but review, and we could still do that. But I think we ought to work on this chapter 3 enough to survive that problem on chapter 3. So let's see what we got in chapter 3. Chapter 3 is really about this stress-strain relationship. See, there's a relationship between stress and strain. And here it is. Called Hooke's Law. This is stress. Well, that's normal stress. And that's strain. That's normal strain. And that is called the modulus of elasticity. And if you make a graph of stress versus strain, what we're doing is this won't hurt us to get a tad ahead and get into chapter 3. And then the rest of the time we'll review chapters 1 and 2 for your test. But see, this is kind of like a graph of X and Y. If you plot up a graph of X and Y, it's just a straight line. You know, Y equals, I don't know, 2X or something. You guys are familiar with that. So you get a straight line. It's just that this value of E here, it's got a fancy name. It's called the modulus of elasticity. It's really big. And so this slope is really steep. It goes real steep. But it's a straight line, as you can see. In fact, if you want to see how big it is, for structural steel, it's 200 gigapascals. This value of E for structural steel is 200 gigapascal. Well, a giga, that's a 10 to the ninth. That's pretty big, you know, giga, 10 to the ninth. The only thing is this doesn't continue on forever. Something happens. Right in here, it starts to curve a little bit. They have names for all this stuff. This right here is called the proportional limit, where it starts to curve. And then it sometimes, depends on the material, will go kind of flat for a while. And then it'll climb up, reach a peak, come down, and then pow, it will fracture. And do they have any, yeah, they have pictures like that. There's one in your book on page 88. They have names for all these regions. This is called the elastic region. All the way up to that proportional limit. And if you take the load off, the body, whatever it is, the piece of steel, or it could be anything, aluminum, or it could even be rubber, whatever it is, it will contract. This graph will go back down to 0, so you'll have 0 strain, and it'll look just like it was before you ever put any force on it. It's not deformed. But see, if you exceed this place right here, it does not go back to where it was. It's permanently deformed. But it has a strange property. When you take the load off, it retreats and contracts, but it goes back with the same slope. it recovers, the way they call it, it recovers elastically. It has the same slope. I tried to draw that with the same slope. Here, has the same slope. And this is called permanent strain. It's been stretched and it's got some strain and it won't go back. It won't go back to zero strain. They call that permanent. It's permanent strain. Yeah. Okay, well, great. And they got different names for this. I already told you this is the elastic region, but everything else is called the, well, I call it the plastic region. Everything else is the plastic region. But I think your book calls it the inelastic region. It's the same thing. Inelastic, plastic. And no, they call it plastic. They call it plastic, yeah. Now they break this plastic region into different parts. This part right here where it kind of goes flat is called the yielding region. And this part right here where it kind of climbs up to the top is called the hardening region. It's the hardening region. And then this part right in here, it's kind of got a romantic name to it. It's called the necking region. You really, when you stretch this material, like a sample rod, for instance, there's pictures of them in your book. You don't really notice any stretching because it's so small. These strains are very small. But you'll start noticing something right in here from the top on down and necking. You'll see that the specimen actually obviously gets narrower there. Now that's the normal stress, normal strain curve. You'll also have a shear stress, shear strain curve that looks just like it. Here's your shear stress, shear strain curve. Now the slope of this elastic region is called E, and it has a name. It's called the elastic, the modulus. We'll spell it here, modulus of elasticity. That's the name of it. This is called Hooke's law. And that's the modulus of elasticity. Now, if you plot up shear stress and shear strain, it's the same deal. You have an elastic region, and you have a yielding region, and you have a same deal. It looks very similar, only we're not talking normal stress, we're talking shear stress. And that equation goes like this, where this thing is called the modulus of rigidity. It's got a fancy name. It's the modulus of rigidity. Did I spell that right? Doesn't look right. You know what I think? I think rigidity is R-I-G-I-D-I-T-Y. Yeah, that's right. Okay, well, great. We understand all that. now they talk about ductile materials and brittle materials. See, steel is a ductile material and it has this yielding region, but there are materials that are brittle and they don't yield. They don't yield. I wonder if I could show you one of those. Let's see here. Trying to find a brittle material. Well, they have one here for cast iron. If you had cast iron, it doesn't have this flat place. It just stops. You can just erase everything else and that's it. Pow, it'll break right there and that's the end of it. It doesn't have this flat yielding region. Okay, well, great. Maybe that's enough theory on that. You'll be reading your book and we'll be studying that more on Wednesday. But what kind of questions could I ask you? Let me see if I can find you a question. Now you need to know something when you take a specimen and you stretch it. Let's say you have something that's like this. And you put forces on it. And later it's going to be it's going to be longer. It stretches. Here, I'll stretch it for you. Look, I made that a little longer. Not only is it longer, but it's a little bit narrower. Does that make sense? It's sort of like, there you go. If you stretch this thing, let's say this is the way it was before you put these forces on it. And then if you stretch it, it will be longer, yeah, and it will be narrower, won't it? Makes sense. Okay, we're going to work a problem like that. Let's see if I can find one here. Okay, now here's one. This is problem 325. We're going to work problem 325. It's on page 115. And now you need to know something about this. I don't know. It gets smaller. It's like a rubber band. If you take a rubber band and you stretch it, it gets longer. But if you look at it close, you'll notice it's narrower. How do you pronounce that? Narrower. Never mind. It's thinner when you stretch a rubber band. If you don't believe me, go get a rubber band and stretch it. But see, there's a relationship called Poisson's ratio, named after a famous guy named Poisson. And it goes like this. The latitudinal strain is he wrote it like this. He used the Greek letter nu. And he said the latitudinal strain is related to the longitudinal strain by his relationship. So what I'm talking about here is longitudinal strain. Let's say this thing was I don't know, 4 inches long. but after you stretch it, it's 4.02 inches long. Yeah, a little bit longer. Of course, this is exaggerating. The longitudinal strain, and we have studied strain. That's chapter whatever 2, I guess. We studied strain. You know what that would be? That would be your 2 inches that it got longer, divided by your original length. The strain is very small. Here's what it would be. 0.02 divided by 4. I'm getting 0.0005, a bunch of zeros, nothings. How'd I do? Wait a minute. Goofed up. It's 0.005. There we go. That's the longitudinal strain. Well, the Poisson ratio for structural steel, it's about 0.35, I think. If you look it up, it's 0.32. So if this is equal to 0.32, and this is equal to 0.005, then the latitudinal strain would be, well, you'd have to take that times 0.32. Here's what you'd get. Does this show up? Yeah, barely. What they call the latitudinal strain, see, that's the strain this way. You understand there's some strain going on this way. They call this latitudinal. Going that way, it's longitudinal. But the latitudinal strain is negative. See the negative? That means it's getting smaller. Remember, stretch that rubber band. And if you know this, if that's given, see, you can look that up for steel. And if you can know that, you can solve that. My calculator says negative 0.0016. Nothings. So now we know the latitudinal strain. It gets smaller by this amount of strain. Now that you understand that, I think we're ready to work problem 325. Okay, well, let me make a little room here. And we'll do that. Need some room here. We told you about Hooke's law. Now be careful. Hooke's law only works in the elastic region. And the reason I'm going into chapter 3 is it looks like I've stuck a chapter 3 question on your test, and it'd be nice if you knew how to do it. I know it's an open book test, but you're not supposed to have to read ahead, are you? Okay, we're going to do problem 325 now, and here's this rod. It's 200 meters long. 200 meters long, and we're going to stretch it. Okay. We're going to stretch it with 300 newtons. We're going to stretch it 300 newtons. We're going to pull on it in tension. It's going to get longer. It originally was 200 millimeters. It's an acrylic plastic rod. The modulus of elasticity is, they give it to us. Isn't that nice? It's 2.7 gigapascals. And they also give us the Poisson ratio. It's 0.4. That's all we know about it. They want to know the change in length and the change in diameter. All right, well, we have Hooke's law. Hooke's law says the See, when you don't know something, when you forget something, you stop, you take a drink of water, kind of stall a little bit, let your mind figure it out. Some people that smoke a pipe, they can tamp it down, and light it while they think. It gives them a time to figure stuff out before they answer. But we know Hooke's law. It goes like this. And we can get the stress because it'll be 300 newtons. Oh, we need the area. Just a minute. Let me read this. It's 15 millimeters in diameter. So you go pi over 4, 15 millimeters. That'd be 0.015 squared. That's our normal stress. It's force over area. We got that. They gave us this. It's 2.70 gigapascal. Hey, we can get they call it longitudinal strain, or we could just call it strain. Okay, we're going to do that. Here goes. Hey, I want you to do it. I shouldn't be the only one having fun here. I'll give you, I don't know, a minute. I want you to find this strain on this, it happens to be acrylic plastic rod. Go ahead, I'll shut up. Well, I think I know what the strain is. Well, let me go to one of my wonderful students here. Let's go to my friend Darren. Darren, unmute. Are you there? Come in,
Yes,
Darren.
sir.
Yay.
I got like 6.28 to the times 10 to the negative fourth.
That's what I got, Darren. I bet we're right. So that would be 3 zeros, 628. And the units for strain are nothings. Well, actually, it'd be 629 if you round it off, but we won't fight over that, Darren. So we got our strain, but that's not what they want. Let me read this. They want the change in length. Well, here's how it works. See, strain is equal to the deformation or the change in length divided by the length. Well, the length is 200. Here, let me circle that. We know the length is 200 millimeters. So this is what they want. They want the change in length or the deformation. That's a little Greek letter delta. A capital delta looks like this. Well, what it means is a difference. See, it's the difference in the length before and after. Okay, I'm going to do that. I'm going to find the change in length. That's what they wanted, right? Yeah. Okay, here goes. I'm going to multiply this times 200 millimeters. Ta-da, I got an answer. make a little, I need some room here. Let's do it over here. If you wondered what we're doing, we're doing problem 325 because I stuck a chapter 3 question on your test, it looks like, and I want you to get it. So it'd be nice if I told you how to do it. So I got I got a change in length of 0.125, I don't know, 8 millimeters. Okay, let's see what else they wanted. Change in length, and they want the change in diameter. Okay, well, we can do that. Now, to do that, though, what we need is the latitudinal strain. See, this here is what the book calls longitudinal strain, going lengthwise, you know. The latitudinal strain, it's going to be negative the longitudinal strain times the Poisson ratio. Well, actually, the way the equation goes is the Poisson ratio, that's a Greek letter nu, alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu. Lambda, mu, nu. Omicron, pi, sigma, tau, epsilon, phi, chi, psi, omega. It's a Greek letter nu, and the way the equation goes is like this. The latitudinal strain, see that's going this way. Do you understand? It's latitudinal. This is longitudinal, that's latitudinal. It's equal to the latitudinal divided by the longitudinal, and there's a minus sign thrown in. If it stretches, it gets thinner. But you know what? If it compresses, if you compress, then it gets thicker. That kind of makes sense. If you mash it together, kind of hard to do with a rubber band, but you could do it with something else maybe. I don't know. Piece of rubber maybe, if you squeezed it real hard, it gets thicker. Okay, well, let's get the latitudinal strain. Now we know this, we just figured it out. Let me circle it. It's right here. And we know this because they gave it to us. They said it's 0.4. So you can multiply those, and we're going to get our latitudinal strain now. We're going to take this here, 0.000629. There's a minus sign you throw in, and then you multiply by 0.4. And here's what I'm getting. I'm getting minus 0.00025516 nothings. Because remember, strain is dimensionless. But that's not what they wanted. They wanted the change in diameter. Well, what you have to do to get the change in diameter, make a little room here. It's the same thing, see? The latitudinal strain is equal to the change in diameter divided by the diameter. Okay. And we know what the latitudinal strain is. It's right there. And we know what the diameter is. It's, well, did they give us the diameter? Yeah, 15 millimeters. This has a diameter of 15 millimeters. So, if you know the diameter and you know the latitudinal strain, you just multiply them. So I'm going to take this times 15. Here goes. Times 15. Well, here's what I'm getting. I'm getting a change in diameter of negative 0.003774 millimeters. That's not much. You would not be able to tell it with the unaided eye just looking at it. Now let's see how we did. I'm going to look at my answers now. 325. We just did problem 325. Okay. And it says the change in your length was 0.126. Where's our answer for the, oh, that's good. The book said 0.126 millimeters. So we did great. And let me keep reading now. This is 325. The book says negative 0.00377. The book says negative 0.00377 millimeters. Hey, that's what we got. We did great. Now you can ace that problem that we give you on your test, and we'll talk some more about chapter 3, wonderful chapter 3 on properties of materials. I'll tell you one last thing, and then we'll go into our review. But first, is there any question on any little thing from anybody? Here's your chance. Any comments or questions?
Mr. Griffin,
Yes.
can you show me the calculations how we get that strain longitudinal 0.000629? Because I was not getting that strain.
Well, maybe I goofed up here. Let me try it here. Let's see. Okay, Mohammed, this length was 200, right?
Yes.
200.
I just want to know how you we get the number 0.00629.
Yeah. Man, I've forgotten how we got it. Just a minute, Mohammed. I'm gonna remember here.
It's on the above equation we got.
Oh, yeah. Here we go. Now this is Hooke's law, and this is stress. Now stress is force over area. You understand the force is 300 newtons, and that's the area. You understand that?
Yes.
And this was given. They said the modulus of elasticity is this. They gave us that. 2.7 gigapascals. Modulus of elasticity, it's given. It's given. And this is the only unknown in this equation. So get your calculator and take 300, divide by pi, multiply by 4, divide by 0.015 squared, and then divide all of that by 2.7 e to the 9th. See, that's e to the 9th. And tell me if you don't get this, Mohammed. I'm going to do it again. Maybe I goofed up. 300 divided by pi times 4 divided by 0.015 squared. Don't forget to square it. Divided by 2.7 e to the 9th. And I'm getting 0.000629.
I'm getting 6.28 e to the power 14 for some reason. I don't know why.
Did you have 0.015 squared?
Yes.
Did you use e to the 9th?
Yes, e to the power 9.
And you're getting something to the 14th?
Yes.
Do it again.
Yeah, I'm gonna do it again.
You're getting the right numbers, but you're getting the wrong exponent. I think I did that right. Well, I got the answer book answer, so I must have done it right.
Yeah, I'm still getting the same thing. I don't know why.
Okay, go through it step by step. Mohammed, put in 300.
Okay.
Divide by pi.
Okay, I did it.
Multiply by 4.
Okay.
Divide by 0.015 and square the 0.015. Don't square the whole thing, just the 0.015.
Okay, I did it.
And then divide by 2.7 e to the ninth. You should get this.
Nope, I'm still getting the same.
What are you getting?
Yeah, can you see my calculator? Can you see my calculator? Mr.
Mohammed,
Griffin,
yeah.
can you see my calculator?
I can't see anything except me in the screen right now, Mohammed.
Mohammed,
Okay, I can read the number. It says 6.287 10 to the power minus 10 to the plus 14.
yeah, Mohammed, I got that too. You need to put the 2.7 times 10 to the 9 in parentheses,
Oh,
or
okay.
else it does some weird stuff in your calculator and it gives you that answer. Try it again with the 2.7 times 10 to the 9 in parentheses.
Okay.
What I was going to say is, Mohammed, throw that calculator away.
Yes, I got it now. It was parentheses. I wasn't putting it. I got it now. Thank you so much.
Maybe you better don't throw it away. Okay,
Thank
good.
you so much, sir. Thank you, Alex.
I want you to know how to do this stuff. Okay, now, if there's no other questions, we're going to have a review now. Okay, review time. There is one homework problem, though, and I think it's due Friday along with your exam. It's on Blackboard. You can read it. But what we're going to do right now is problem. It's on page 55, but I'm going to change this problem. And I like to do this on exams sometimes. I'll take a problem that we've studied and I'll change something. So this is review, but I kind of got that gut feeling that maybe we need this. Now what this is, it's on page 55. Let me find it here. Yeah, it's problem F114. But I'm going to change it. Now it's a 3, 4, 5 triangle. So let me draw that. I'm going to draw it. And you know, I could do it to scale. That would be cool. We'll do it to scale. All right. And I can even get the angle because it's a 3, 4, 5 triangle. And I know the angle. I've memorized that. It's 3687, isn't it? 3687. It's a 3, 4, 5. See, this is 2 feet, 2 feet. There's 3 feet here. Let me put that in there. That's 3 feet. And what you have here is what they call a rocker. That's a rocker. What you have here is a smooth pin. And what I'm going to do to change this problem, let me put some letters on here. This is A, B. We're going to have C, D here. We'll put that in there. A, B, C. No, that's D, E. C is over here. What I'm going to do to change this is I'm going to put the force in a different place. It says there's 600 pounds, but they have it over here. I'm going to put it right here. I can do that. It's my problem. I can do what I want. I'll put the 600 pounds right there. And now what we're going to do is, well, we'll find out all kinds of stuff. It's a review deal. Whenever you do this, you know the drill. By the way, they said the diameter at pin A is 0.25 inches. We'll make a note of that. There's a diameter of a pin here, 0.25 inches, and this is a double shear. You know what I'm talking about? Double shear. It's got 2 of those brackets, not just one bracket. It's got 2 brackets there at A. Now here's how you do these problems. You draw a sketch to scale and you measure stuff. See, I measured that 2 and I measured that 2. And this is a 3, 4, 5 triangle. So you know how long this is? That's 2.5 feet. That's 2.5 feet because it's a 3, 4, 5 triangle. And you know what this would be here? This would be 1.5 feet, wouldn't it? Do I need to explain how I knew that this was 2.5 and that's 2.5 and that's 1.5? You're okay with that? You all on board with that? Okay, we're going to find out everything that's going on with this thing. We're going to find the internal forces. See, first though, you've got to get the external forces. Okay, well, let's do that. Now, if this is a rocker, then this force here can only go that way because the rocker can't give you any forces up and down. It would just sort of wobble there, see it? So you have a force there. You could give it a name. I don't know, B, it sounds like a good name. And you're going to have some forces here at A. I don't know which way they're going yet, but you could have forces in both directions there at A. There's nothing at C because I changed the problem. The problem had 600 pounds at C, but I changed it. That's what I often do. Okay, now how do you find these external forces? Here's the drill. You draw the sketch to scale, you measure angles, you measure distances, you draw all the forces in red. Does that red show up? Well, kind of. You put the forces in red. And then you use these equations. The most important one is this one here, the sum of the moments. Take them about point A. And you'll have a minus 600 pounds times 2 feet. Why is it minus? Let me ask one of my wonderful students here. Let's see. How about, oops, I pushed chat instead. That's a goof up. How about Samuel? Are you there? Can you hear me, Samuel?
Yes, I'm here.
Thank you, Samuel. How come this moment, 600 pounds times 2 feet, is negative, Samuel? How come it's negative?
It is going it is going clockwise.
Yes, that's the right answer. Good going. Good going. It's clockwise. And then you have a plus b times 3 feet equals 0. And we just wrote the sum of the moments about point A. There's only two. There's this force here and that force there. I put them in red. I put them in red so they kind of jump out at you. So you see that they're in red. You can't miss them. You don't want to miss any. You'll get the wrong answer if you leave any out. But if you solve this, I get B is 400 pounds. I bet you can do that. I bet you can solve that and get 400 pounds. What do you think? 6 and 2 is 12, 3 and 12 is 4. Yeah. Well, all right. And then you can do the sum of the forces on the whole body. Like in the X direction, for instance, you got 400 going to the right. I guess this A must be going to the left. What do you guys think? It's got to. Look here. So we got 400 pounds going to the left. Good deal. And we're done. Ta-da! We are done. The sum of the forces in the X is 0. You can do the same thing in the Y direction. The sum of the forces in the Y direction. Well, you got 600 going down. Hey, I know what going on here today. Look here. It's got to be 600 pounds going up, huh? Yeah, there's only two forces going up and down. So you don't even need me to write it out, do you? Now, I told you this, but I don't know if you guys remember. You're supposed to look for 0, 2, and 3 force structures. We'll just say structures. Well, this whole structure is really a 3-force structure. These are really just components. See, the actual force acting there, that actual force acting there would be, well, I don't know what it would be, but it would be 400 squared plus 600 squared, wouldn't it? Okay, well, let's do that. Let's find that force. Let's see. 600 squared plus 400 squared. I hope I'm boring you, because if I'm boring you, that means you understand this stuff. Hey, guys, I'm getting 721.1 pounds. Now, in the problem, they asked for the shear stress Was that point A there? Yeah, yeah, that's A. I think I erased the A. If you want the shear stress at A, what you have to do is you have to take the 721 pounds, because that's the actual force. Do you understand? These are really just components. And then you have to divide by the area. But see, if it's double brackets, you've got two areas, and the areas are pi over 4 diameter, 0.25 inches squared. That's it. I'm going to shut up for a tiny minute, and I want to see if Mohammed can get this before he throws that calculator away. Try this, Mohammed. I want to see if you can get, and the rest of you. I'm going to do it too. We're going to get the shear stress. Here goes. Mohammed, what did you get this time?
I got 7,345.16.
That's what I got. I got 7. Now, if you want to be fancy-wancy about it, you can go 7.345 KSI. Or you can report it like Mohammed did and say 7,345 PSI. You all know what a PSI is. It's a pound per square inch. And a KSI is a kilopound per square inch. Okay, great. So what? Well, I want us to find the forces on each member. We did all that, and we're pleased with ourselves. Oh, but now wait a minute. We were supposed to look for 0, 2, and 3 force members. There is no 0 force member. They all have forces on them. Now, I think that this ED here is a 2 force member, because it only has these 2 smooth pins. There's forces acting on each end of that member at the pins. So it's a 2 force member. Let's talk about ED for just a minute. There's room down here. Now, ED is a 2 force member. Y'all, a little Southern talk, y'all agree with me on that? If anybody disagrees, speak up. But I think it's a 2 force member. Did you know two force members come in 2 kinds? There are 2 different kinds. There are 2 kinds of 2 force members. ED is a 2 force member. We're going to go to one of my exceptionally bright students. Julian, unmute. Are you there? Julian, are you there?
Yes, I'm here.
Julian, do you remember the 2 different kinds of 2 force members? He's thinking. Julian is thinking. There's 2 different kinds.
Is it tension? Can you hear me?
Yeah. Did
Is
you
it
say
tension and
tension?
compression?
Yes, that's it. Good going, Julian. Proud of you. We know that there are two different kinds. There's the tension kind and the compression kind. Okay. So let me write that. I need some room here. We'll get rid of all this. There's this ED thing that we're talking about here, or we could call it DE, doesn't matter. It's either tension or it's compression. And you guys know the difference. Tension is when you stretch stuff, right? And compression is when you are pushing on it and you're trying to make it smaller. I think it'd be fun to vote on this. It's kind of hard to vote. I don't know how to work this computer here, but I don't want to take up too much of our valuable time, but let's just go through the list here. Let's start with Nicholas, Alex, Ashley, and Ben. What do you guys vote for, tension or compression? Nicholas, Alex, Ashley, Ben.
Think it's gonna be compression?
Okay, we have one vote from one of our students for compression. Nicholas, Ashley, go ahead.
Compression.
We have two votes for compression. Well, it's open to everybody. There's Ben, Nicholas, Alex.
I think it's compression.
We have 3 votes for compression. And we have Samuel, Mohammed, Julian, Jackson. Go ahead and vote.
Compression as well.
I also
Okay.
think compression.
Was that compression?
Yeah, compression.
Yes, compression.
We have 5 votes for compression. What about tension? Nobody? Is there anybody out there that wants to vote for tension? Well, I know we got more than 5 students. Some people haven't voted yet. If you'd like to vote, now's your chance.
I vote compression.
Okay, there's 6. Anybody else?
Compression.
That's 7. I didn't count all the students here, but I think we still have more than 7 students. Okay, is that it? Anybody brave enough to go against the herd here? See, there's a phenomenon known as peer pressure, the herd, where you sort of lose your identity and you go with the mob. You know what I'm saying? Now the mob says compression, and nobody says tension. But if it's tension and you're right, well then guys, here's the thing. There's stuff that's right and there's stuff that's wrong. In this case here, did you know there are things that are not decided by a vote? There are things that are not decided by majority vote. There's stuff called right and wrong. There's stuff that's correct and incorrect. And in this case here, it is either tension or it's compression, and it doesn't matter a whit if everybody says it's compression and it turns out to be tension. It doesn't matter that everybody voted. Do you understand? Voting is not how reality is determined. This is a really important concept. If you guys can just get a hold of this. Not everything is determined by a vote. Okay, well, we're going to find out. We're going to find out what it is, but the herd says it's compression, and usually, no, I wouldn't say usually, but a lot of times the herd is right. Okay, a lot of times the herd is right, but not always. All right, well, let's do it. Now, how would you do that? Well, to find internal things, see, tension and compression are internal. You have to break this thing into parts. Okay, well, let's see how we're going to do that. Well, one way is we could look at this AEC thing. Let me draw it for you. Here's AEC. There's AEC. And now we know we have 600 going up here and 400 going that away. We know that for sure. 600, 400 doing, and we also know there's 600 doing this. But what we don't know is this here. Now see, if it's pushing, that's compression. If it's pulling, that's tension. Do you understand? It's either pushing or pulling. We don't know yet. But it can't be both. It's one or the other. Now what you do is you take your moments about C. Here we go. The sum of the moments about C. Now I don't know what's going on at C. There could be forces going all sorts of ways. But see, we don't care because it's a smooth pen. And smooth pens can't give you any moment. So that can't give you any moment. You see that 400? That does not give you a moment about C. Does anybody know why the 400 does not give you a moment about C? Let me ask somebody.
With a point.
That's right. It goes through the point. 400 goes through the point. Forces that go through a point do not give you a moment about that point. But the 600 does. Now let's see, that's clockwise. So you got minus 600 pounds times, well, it'd be 4 feet. Because see, if that's 2 feet and that's 2 feet, that 600 there is got 4 feet. Then you have a plus 600 pounds times 2 feet. Now that's positive because that's counterclockwise about C. And it looks to me like you've got to have pulling here. You've got to have, in fact, you need another 600 pounds at that 2 feet to equal 0. You know what? The crowd, the herd was wrong. This thing is a tension member. Can you see that? Because tension pull, let me tell you this, tension pulls and compression pushes. Compression pushes, tension pulls. You've got to have 600 pounds of tension pulling. This is a tension member. The herd was wrong. Let that be something that will sink into your head. You can have 10,000 people saying this is the way it is. And there could be one person that says, no, this is the way it is. There are things where that one person can be right and those 10,000 are wrong.
Professor, I have a question.
I'm listening.
The way I kind of broke it as like that, but I did the moan about A, and then I got compression because I only had 600 down and I had to have 600 up.
Well, the problem is, did you include the forces at C?
I didn't think there was any at C.
There is, and we're going to find them. And that's the problem. So let's find them. So right now, we're going to find the forces at C. Well, we know the sum of the forces is 0 any place, on the whole structure or on any member or on any pin, we know the sum of the forces is 0. Now let me think here. We got 600 going up, 600 going down, 600 going down. So what do we have to have at C? Think about it. 600 goes up, 600 goes down, 600 goes down. What do you have to have at C? Well, you have to have 600 going up. The sum of the forces have to be 0 in the y direction. Does that compute? If you have 600 and 600 going up, and you have 600 and 600 going down, does that compute? It does for me. Now let's do the forces going this way. You got 400 going this way. So what's this got to be? Well, it better be 400, hadn't it? If you have 400 pulling to the left, don't you have to have 400 pulling to the right? Well, yeah. Where do these forces come from? Where do those forces come from? Now, let me ask one of my wonderful students here. Jackson, I don't think I've picked on you all morning, Jackson. You see those forces acting at C there on this body, AEC, Jackson? Say hello, Jackson.
Hey, yep.
Yeah, you're there. Where do these forces come from, Jackson?
From the pin.
That's not the answer the teacher wanted, Jackson. They're acting on the pin, but where do they come from? Something has to cause them. That's okay if you don't know, but see, I'm making them struggle here. I want you to know that they come from this member B, D, C. They have to come from someplace. They can't just come from outer space. There is no external forces, do you understand? We are looking at this member here, this member A, E, C. And we're looking at the forces on it. And these forces have to come from this other member. Now let's draw the other member. And we need some room. Here's some room up here. We're going to draw that member. Here you go. There it is. And I can come down a little further. There we go. Now this is member B. I know there's this rocker here. This is B, D, C. And we're going to put the forces on it. Now this 600 is an external force, but you see this 600 here? That's a tension force on this AEC. So there's a tension force at D, but it's equal and opposite going this way. See, tension always pulls. And so you see that 600-pound pulling on E caused by DE? Well, there's a 600-pound at D tension force pulling on BDC caused by ED, if that makes any sense to you. And here's B, and we know what that is. That's 400 pounds. Now let's look at these forces here. You see the 600 pounds? Well, that's the force on AEC. Where does it come from? Well, it comes from this BDC, only it's equal and opposite. It's going this way. See that 600 pounds? And see that 400 pounds that's going that way? Well, that's going this way. There's the 400 pounds. Now let's see if all of this makes sense. Do the forces add up? The 400 going that way and the 400 going that way. Are the sum of the forces zero in the x direction on this member? And you should be nodding your head. Yeah. Look, 400 going to the right, 400 going to the left. What about the sum of the forces in the y direction? Well, look here, you got 600 going up and 600 going down. Yeah, they add up to zero. How about the moments? Let's look at the moments. Take the moments about, I don't know, B would be fine. Take the moments about B, and we're just doing this member here, this BDC. Well, you'd have 600 pounds times this distance here, which is 2 feet. Do you understand? This distance from here to here is 2 feet. It's 2 feet. 600 pounds times 2 feet, that's positive. Then you have a minus 600 pounds times 4 feet. See, this distance all the way over to here is 4 feet. See, from here to here, it's 4 feet. But you've got plus 400 pounds times 3 feet. Now the question is, does that add up to zero? Well, I don't know. I don't know. Let's see. 600 times 2 is 1,200. And then 400 times 3 is 1,200. That makes 2,400. 600 times 4 is, well, that's a negative 2,400. Yeah, you know what? It adds up to zero. That's good. That's the forces on that member. Now, one last thing. Before I show you this, any comments or questions from anybody? Oh, gee, we only have about 6 minutes left, and we're just starting to have fun. I don't guess anybody has any questions. Well, okay, what I wanted to show you is this business about look for 0, 2, and 3 force members. We never looked for 3 force members. You see this whole structure here. You know what? It's a 3 force member. These are just components. You have that force, and that force. What do you know about 3 force members? And let me go to somebody here. I can't remember if I've picked on Darren yet. I think I have. Darren, have I picked on you today?
I don't mind being picked on again.
That's the attitude. I love that attitude. Darren, what do you know about 3 force structures? They're either something or else they are something else. What are the 2 things that got to happen with a 3 force member, Darren?
Shoot. I literally just had that, and then you wrecked my train of thought. Oh, man.
I'll give you a hint.
Honestly, I lost it. I'm so sorry.
Darren, I'm going to give you a hint. The forces are all either parallel, which they certainly aren't in this case, or else...
concurrent, right?
That's it. They're concurrent. That means that these 3 forces have to go through a point. Now, we have plenty of time. I think I'm going to shut up and I'm going to let you, hopefully you've tried to draw this in your notes. I know you're all taking excellent notes of my wonderful lectures. Go ahead and find the concurrent point. What if I ask you that on a test? Where's the concurrent point? That's the point where all the forces go through the same point I'm going to shut up here for 30 seconds. I want you to draw the point that those three forces go through. Draw it. Okay, 30 seconds is up. Here we go. We're going to draw it. Now, why don't you draw a line through this force here? See that line there? We drew a line through it. Draw a line through this force here. We drew a line. See where they cross right there? See that force right there? Guess what? Guess what? It has to go through that same point because this is a three-force structure. Now let me show you something interesting. We can get this angle here. This distance here is 2, as we all know, and that distance is 3. We can get that angle. What is the arctangent of 2 over 3? 2 divided by 3 is arctangent. Guys, I'm getting 33.69 degrees. 33.69 degrees. Let's measure that. Get your protractor. I want you to go to the store and buy a protractor and put it on here and see what it says. Well, it's supposed to say 33.6 degrees, and it's, yeah, mine's a little off. It's more like about 36 degrees. I'm a couple of degrees off because I'm sloppy. But you can measure that, see? Isn't that neat? That's the concurrent point. Now let's look at these two here. I've got another 2 minutes left. You see this? This is just a member. It's member BDC. There are only 3 forces acting on it. It's a 3-force member. It has a concurrent point. Draw a line through this force. Draw a line through this force. Do you see where that is? That's the concurrent point. You see these right here, the 6 and the 4? If you were to draw that force and come on down here, it will go through that point. You see this member here? It's really a 3-force member. I know that you've got these 2 forces, but see, they combine to give you a force of 721 pounds. See these 2 here? They're the same numbers. They combine to give you a force of 721 pounds. These 2 here come down here. These come down here. There's your concurrent point. And see these 2 here, they go this way. They come down here and they go through the same point. They're all 3-force members, and they all have a concurrent point. Well, I had enough fun there with that, and I hope that helps you on your test. I'm going to sign off now. Any last words? Here's your chance.
Professor, when should we expect to see that test?
It should be on there by now.
Okay.
It should be. We had trouble.
It's on Blackboard.
It's on Blackboard. Go to Unit 1.
You said Stu.
Go to Unit 1, go down to the bottom of all that stuff in Unit 1, and it should be there. There's a link.
It's on there.
Did anybody find it? Should be a link.
Yeah, I see it on there.
Yes,
It's on there. Enjoy. And I will see you Thursday. What is today? It's Tuesday? Yeah. See you Thursday at 9:30. Bye-bye.
See you.
Bye-bye.
Bye.